Math, 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 math. No, it's physics. Okay, today is actually not really a new math topic at all. It is an application of the math to a very important physical problem, and that problem is, of course, diffusion, which is kind of a big deal. Now, the idea I want to introduce here, the physical concept that is very important, is the idea of a continuity equation. If you've heard of this before, great. If not, let's get started. A continuity equation is an equation that is related to a conservation law. Now, conservation laws you've seen before. You've seen conservation of energy, conservation of momentum, like these kinds of things, and conservation of mass, conservation of you name it. So each of those conservation laws has an equation that goes with it that is not just amount of thing equals constant, but that describes the flow of that thing from one place to another or one time to another in the world. And so these are the continuity equations. These are the equations that tell you how conserved quantities move around. And the form that they all have is this sort of form where you have an amount of flow into or out of your system, and that flow in or out tells you the change in that quantity. And if you look at this just on the surface, you're like, well, yeah, I mean, what is there even to say here? If something comes into your system, then the amount changes. Well, that's true for conserved quantities, but so many things in the world do obey conservation laws that sometimes we lose track of the fact that there are quantities that are not conserved. One example is photon number, which might sound weird and quantum mechanical, but let me bring it back to daily life. You ever turn on the lights and then suddenly there's light where there wasn't before? You can just create photons. You can be like, okay, I have no light and now there's light. And you do this by converting other forms of energy into that light energy. So photon number is not conserved. You can just change the amount of light in a system. Now, a couple of conserved quantities that have these sorts of continuity equations, I have a couple of physics 140 examples here. Newton's second law is actually a continuity equation. It describes the flow of momentum in mechanical systems. It says, okay, if the amount of momentum is changing with time, that means there is a force acting. The amount of momentum into the system is coming from this force. And then that relates to the conservation law that is Newton's third law, which is that, if one body loses momentum, then the other body has to gain an equal amount of momentum. Then we also have continuity equations in fluids. You see this in this A1V1 equals A2V2 business. This is talking about the flow of fluids in a pipe. So if you have a pipe with some cross-sectional area, that's the A, then if you make that cross-section smaller, the flow rate, the speed of the fluid goes up because the total amount of fluid is fixed. Fluid goes in, fluid goes out. You don't just have water magically disappearing in pipes. It enters the pipe and it leaves the pipe. So in order for that quantity to stay constant, the amount that flows into a certain cross-section of the pipe, you need flow out of that cross-section of the pipe. And if the area is changing, that's going to result in a change in the flow rate so that you have a constant total. Cool. So those are two examples. Now, Fick's first law is also a continuity equation. This you should have seen in the intro MSc class. Now you see it in this introductory form in a pretty simple differential form, and that is telling us that when you have a concentration gradient, so that's dc dx, then that leads to some flux of particles. Or another way to say that is that when you have particles moving from one place to another under diffusion, then you know there must be some difference in concentration between the two places that leads to that motion of particles. And the D, the diffusivity coefficient, that's the strength of that proportionality. Bigger Diffusivity coefficient means that a given concentration gradient leads to a greater flux. Looking at the units of these things, I know I've really been pushing the dimensional analysis lately. It's important, especially when you're doing coding, because the computer will not do units for you unless you have software, or if you have, code base, if you have a library that is built for units. Otherwise, you're on your own to keep track of these things. So looking at the units here, the dCdx term, let's start with that. So the concentration itself, that is just molarity. This is moles per cubic meter, or moles per liter, same thing. Not saying that 1 liter is 1 cubic meter. I'm saying that they're both volume measures. So you have moles per volume, and that is the concentration C. And then you also have a 1 over meters from the derivative. I know I said this before recently. I'm going to say it again because it's a big deal. Derivatives have units. It's the units of the variable you're differentiating with respect to. ddx, the x is in the bottom. That's a 1 over distance, so it's 1 over meters from that derivative. Then on the left, the flux here, fluxes are always going to be something per square meter per second. And this is because what a flux indicates physically is the flow over time. So as time passes, we have a motion of something through a surface, that surface has some area, and the movement, in this case of concentration, so the movement of molecules through that surface, is the concentration flux. So that's the per meter squared per second. And then the numerator is moles because it's moles of whatever substance we have moving through that surface. The diffusivity coefficient, this meter squared per second, that's just the proportionality that makes the units work out. I wouldn't overthink that one. So there's our continuity law. This is saying that if I have a concentration gradient, then that means that particles are going to flow as a result of that gradient. But the real world is 4-dimensional. It's 3 space dimensions, 1 time dimension. So we can't just have one single regular derivative. We have to describe this relationship with partial derivatives, taking into account the dimensionality of our universe, not the pretend training wheels intro MSc universe. And so here it is. The derivative becomes a gradient. Now, this is really helpful actually for thinking about the physics of it as well, because when you remember the meaning of the gradient operator, that gives you a vector pointing in the direction of greatest rate of change. So the gradient of C, this is saying, give me a vector that points in the direction where concentration is changing the most steeply. And what's going to happen then is that you are going to get a flux in that direction. These two vectors are directly proportional to each other. They're pointed in the same way. So now we say, okay, when I have concentration gradients, then the direction of the flux, the direction where the particles move, they're going to move from higher to lower concentrations, and that's what is coming out of the negative sign here. So the driving force for the flux, the cause that makes the flux happen, is the concentration gradient. And that's not something you get from the equation. That's something you get from your understanding of the world. These other continuity equations, it's a similar problem. You just have left side equals right side. You don't know which one is the cause and which one is the effect from the equation itself. You have to know how the world works. If we're looking at Newton's second law, F equals ma, F equals dp dt, you can't just be like, accelerations cause forces. Well, no, forces cause accelerations. But in the equation itself, you just see left equals right. So you have to understand that as part of the interpretation of the meaning of the math. So we have this relationship that a gradient of concentration is going to cause a flux of particles, and that they are going to move from areas that are more concentrated to areas that are less concentrated. And I'll go back for a second here. The other reason to think about this physically in this way is to think about the molecules themselves. You've got a bunch of little molecules of substance bouncing around. They're warm. We're not doing anything at 0 Kelvin here, no absolute zero. Things have heat. They have this random thermal motion. And so if you have a lot of molecules in one place and they're all moving and bouncing and bumping into each other, having their little molecule party, what's naturally going to happen is that if they're moving around randomly, which is what heat is random motion, then they're going to tend to end up in places that used to have less concentration. And they are going to tend to move away from places that had originally higher concentrations. So thinking about the movement of the molecules themselves and what happens when stuff is moving and bouncing around and when particles are bumping into each other, that leads you to the same conclusion. Okay. So now we're going to look at how things change over time, because I've sort of hinted that. Let's explicitly put time into the equation now. And we're going to do this by taking a time derivative. So partial dc dt. And this is going to come from the divergence of the flux. So we have to revisit divergence for a second. The divergence of a vector field, just in general, just the meaning of the math, divergence means, is my vector field on the whole moving into this location, or is it moving out of this location? If the divergence is positive, then your total vectorness is pointed outward. And if your divergence is negative, then the total net amount of vector is pointed inward. So knowing that, you can start to put some interpretation on this equation. You can say, okay, I have some particle flux J. Particles are moving in a certain direction from point A to point B. Well, if mass is conserved, and if the total number of particles in the universe is going to stay constant, then as they are moving from one place to another, the concentration in each location changes. That's the dc dt here. So looking at the sign for a second, okay, if my flux is positive, sure. If my divergence of the flux is positive, let's look at this combination actually. That divergence is positive in this example, so that means we have a net outward flow of vector. So then the whole right-hand side is negative because we have negative times the divergence. So this means we have a outward flow of particles. That should mean the concentration decreases, and that's what this minus sign does. The time derivative of the concentration is negative because we have an outward flow, an outward flux of particles, which is calculated by taking the divergence and then finding out that the divergence is positive, so outward flow, so multiply that by -1, and we have a decrease in concentration. That's conservation of mass in the language of differential equations. Here's the simple version of all the words that just came out of me. An outward flux of words through the surface of my mouth hole. All right, well, okay, let's keep going with the math instead of trusting me with words. When time is passing, then, we get to Fick's second law. So here was the conservation of mass equation that I just wrote. And what we're going to do is just substitute in the expression for the flux that is Fick's first law. So we have a continuity equation for molecules, for molecule density, and then we're going to combine that with conservation of mass. When we put these two things together, the negative signs cancel out, and we get this lovely expression on the right, the divergence of the gradient of the concentration with the diffusivity coefficient in there. And if, not always true, but if the diffusivity coefficient is a constant, then this simplifies. If diffusivity coefficient is not constant, which can happen in reality, it can depend on temperature, it can depend on pressure, it can depend on these other sorts of environmental variables. If it's not constant, well, this is your final form. Hooray. If it is constant, then it's just a coefficient, a numerical coefficient, and you can move it outside of the derivative. This is nice because then we have del dot del C. So the divergence of the gradient is the Laplacian. Hooray! I'm excited about that. Also, I've just written explicitly here that the concentration is a function of position and time. That at every point in space, there is some concentration, and at every moment in time, there is some concentration at each of those locations in space. And apparently, this means that the time derivative of the concentration at any point in space-time is going to be determined by the Laplacian, the spatial derivatives, spatial second derivatives of the concentration at that place and time. And then there's some constant of proportionality between them. Okay, weird? Well, no, actually. What we have to do is go back to the interpretation of what the Laplacian tells you about a function. To calculate it, here's the expression. It's, remember, second x derivative plus second y derivative plus second z derivative. Not as a vector equation. This is a scalar equation. Concentration is a scalar, and we are taking different operations on the concentration. Each of those individually is a scalar quantity, and we're adding them all together. We are combining those into one single expression. We are not keeping them separate in some x component, y component, z component vector business. Just one total amount, because concentration itself does not have a direction. I can't be like, yes, the concentration of this hydrochloric acid is 3.7 molarity east or 2 molarity up. Like that just doesn't, that's not what that thing is. It sounds weird to even say it. It's 3 molarity. It's 3 moles per liter. So this is a scalar equation. And what the Laplacian tells you about a function, reminder from the vector derivatives lecture a few days ago, is that the Laplacian tells you about averages in an area. If your Laplacian is positive, your function is curved upward, concave up, and that means that because it is curved upwards, like here's our point of interest, here's the function, this upward curving function, that means all of the regions around the point of interest, in here and in here, the value of the function is greater than the value of the function at the point that we're looking at. So that means that the average value of the function nearby this point is greater than the value of the function at this point. This is really useful for understanding diffusion because what it's telling us is that concentration is going to flow from higher areas of concentration to lower areas of concentration as time passes. If the Laplacian is positive, curved upward function, that means that according to this equation, the time derivative of the concentration is also positive. So the concentration will increase with time when the Laplacian is positive. And the concentration increases with time because nearby our point of interest, the concentration is greater in the area around it. And so that concentration is going to flow toward our point of interest from high to low concentration. Hooray. So this is why, well, I don't know if I should say this is why, but mathematically, this is how we quantify this smoothing out, averaging out effect that the diffusion equation describes. That as we allow substances to diffuse around in the world, they are going to end up going from high places to low places, such that after a lot of time has passed, things are going to achieve some sort of uniformity in equilibrium. So that's the diffusion equation. Cool. Now, this question was asked by a student, and it was such a good question, I actually wanted to dedicate a slide to it, which was the title here, Where do PDEs come from? Well, you see, when two equations love each other very much, then, okay, no, that's actually not where PDEs come from. They come from, surprise, thinking really hard. But, that's not the whole answer. The thing is, you can think a lot about the world. You can sit down and ponder and focus and consider and philosophize. And unlike what the ancient Greeks would have us believe, you cannot, according to the modern understanding of science, you cannot figure out the nature of reality just from thinking about it. You need to engage with the physical universe to study how it actually works, because how you believe it works and how it really works might not be the same thing. Or they might qualitatively agree, but the numbers, the quantitative extent might disagree. And this means that you need data. You need to perform experiments, you need to perform measurements. Now, to give a little bit more of a concrete example here, why is it that in the diffusion equation, it's just the first derivative of concentration with respect to time on the left? Why isn't it the second derivative with respect to time? Or why isn't it the square of the time derivative? Or why isn't it the square root of the Laplacian? I mean, there's all sorts of other equations that would have the same physical reasoning. The physical reasoning here is concentration goes up when the concentration nearby that point is higher. Sure, seems reasonable, but there are many different equations that would describe that same relationship, but disagree on the exact numerical values of how much things change. And that is how these PDEs are developed to model the world around us. Is, yeah, you sit down and you think and you consider relationships and you think about what kinds of rates of change influence each other and which variables cause which other variables to change. And then you go out and you do a lot of experiments to get enough data to find the right function that fits the data. So when Fick was developing these laws for diffusion, they were published in 1855, I want to say. There was a lot of other stuff happening in the world at the time. So like the US is getting ready for civil war. Brahms is becoming famous as a composer. We're like 20 years past the death of Beethoven, so we're solidly in the Romantic era musically. We're getting close to the time of the Meiji Restoration in Japan, when Japan like opens up to the rest of the world and doesn't have closed borders. So all of these different political and artistic and cultural things are happening all around the world, and Fick is sitting in a laboratory measuring diffusion in, you know, beakers and jars and vials and doing chemistry. It's just fun to remember that all of history is happening all at the same time and all of these timelines are crossing with each other. But the history aside for a second, the point is he did a lot of experiments and extracted these equations from data sets showing which quantities were directly proportional to which others and what was squared and what wasn't. And that is where PDEs come from. Great. That's everything I wanted to say. This is the only video for today, so I let it go a couple minutes longer, but I hope you found that interesting. If this is your first introduction to diffusion in a three-dimensional sense, I hope it was useful to you. If you've seen this stuff before, well, maybe you got a new perspective on it. But that's all of that. I'm going to sign out, and then I will see you in class.